Okay, good morning everybody. I think that we can start. I'm Giacomo Falcucci from the University of Tor Vergata. I will chair this plenary by Dr. Lauricella, Models for Electrospinning Computational Experiments. Dr. Marco Lauricella is a colleague and a friend from the Institute for Applied Calculus Applications from the Italian CNR, and he will give us this interesting talk this morning. So, please, Marco, the floor is yours. Thanks very much.
Thank you. Thank you. Good morning. It is a pleasure to be here, and I would like to thank the organizer for giving me the opportunity to be here today. The title of my presentation is Models for Electrospinning Computational Experiment. I also would like to acknowledge Dario Pisignano, which was the PI of the ERC project NanoJets, finished in the 2018, and where this investigation started. Also, I would like to acknowledge Sauro Succi, leading the COPMAT project, for ensuring the growth of this investigation within the COPMAT framework. I would like to start outlining the main ingredients of the electrospinning process. The electrospinning is mainly used to manufacture nanofibers, which have the peculiar feature to present a cross-section spanning in the range from the micrometers up to the nanometers, so spanning really across different scales of lengths. Usually, nanofibers are made by several polymers. Here I present two notable examples. One is the polyethylene oxide, another is the polyvinyl pyrrolidone, but there are several others that can be used in this manufacturing process. The high surface to volume ratio and so the high porosity are probably the main feature of the electrospan materials. As a consequence, the nanofibers can be used in the context of filters and membranes. For instance, electrospan materials are suited for water filtration, blood filtration, bioseparation. Further, due to the high porosity, electrospan material can be used also as electrodes for fuel cells, lithium-ion batteries, solar cells, but also, for instance, in the context of the catalysis. Moreover, electrospan materials can be also used in the context of the tissue engineering, for example, for manufacturing protective clothes and artificial skin. Here, I want to show a general sketch of the process where we start from a polymeric solution with a solvent, which is usually a mix of water and alcohol. Then this polymer solution is positively charged by an electric generator, which has also the role of ensuring a difference of electric potential between the nozzle and a collector. Hence, the polymer solution injected at the nozzle is stretched by the pulling external electric force, and the filament is collected on a conductive plate. In the process, we can recognize two main stages. The first is characterized by the formation of the so-called Taylor cone, where the jets start. Hence, we observe a straight initial path where the filament is strongly stretched by the external electric field. Then, in the second stage, the jet radius of the filament rapidly decreases and complex bending instabilities start to appear in the jet path closer to the collector. And shortly, we will see that the bending instability are due to the electrical repulsive force of the charge lying on the jet surface. But let me now focus on the first stage of the process. We can observe that the polymeric fluid is strongly stretched by the electric external force, which is overcoming all the other possible force terms. For instance, if we compare the electric force just outside a perfectly conductive liquid droplet to the capillary force, we can observe that the ratio between these two force terms, also referred as the electrical bond number, takes a value larger than 1, usually larger than 10 in this framework. As a consequence of this intense electrical field, the jet endures a high velocity value. This high velocity provides a larger value in terms of the capillary dimensionless number, which as a consequence is larger than 1. It is also explained why we do not observe the dripping regime, but we observe the jetting regime. Moreover, we have to consider that the presence of the polymers in the solution provides usually high viscosity and high elastic modulus. As a consequence, we are in presence of an intense longitudinal stress. Here is a sigma. And in practice, if we compare this with the capillary pressure, we can observe that the ratio usually is spanning from 10 up to 100. And this fact itself also stabilizes the jetting regime. Hence, this stage is characterized by a straight path of the jet. We now proceed to inspect probably the most peculiar characteristic of the second stage of the process. The jet radius decreases under the effects of the stretching force. As a consequence, the longitudinal stress also decreases due to the smaller cross-section area of the jet. Hence, we observe the presence of the bending instabilities. In this process, the bending instabilities play an extremely important role, since these instabilities increase dramatically the path described by the jet traveling from the nozzle to the collector. As a consequence of this larger path, we can observe a further decrease in the jet radius and an increase in the surface to volume ratio of the final electrospun materials. The bending instability are usually explained in terms of the Earnshaw theorem. This theorem states that a straight chain made of electrical charges of the same sign cannot be in equilibrium along a straight line, but any small perturbation perpendicular to the jet axis triggers a perpendicular repulsive electrical force which bends the segment outside from the jet axis. Until now, we have shown the main ingredients of the underlying physics, but let me now introduce which are the still open questions that can be addressed by computational investigation. Although several experimental studies have spanned parameters and electrospinning process setups, it is extremely difficult to catch important observable, as for instance the shear rate that can be tuned to obtain for instance different porosity of the electrospun materials. Further, it is difficult to provide the rational design to optimize the feature of this material, for instance introducing new experimental setups. Moreover, it is also difficult to control the bending instabilities in order to optimize morphological and topological feature of the material at the collector. For instance, the orientation of the fiber. We have also another important issue. The scales involved in this process are extremely different. The initial cross-section radius of the jet is around hundreds of micrometers, and during the stretching process close to the collector, we can observe that the jet radius value can also reach few nanometers. On the other hand, the typical distance between the nozzle and the collector is of the order of 10-20 centimeters. So we have several length scales involved in the process at the same time. As a consequence, it's extremely difficult to find a unique computational tool able to deal with all these different scales. This problem is intrinsically multi-scale. Here, we rely on two main computational methods to model this process. The first is the lattice-Boltzmann. The second is the Lagrangian particle dynamics method. These two tools are applied on different scales. So we will use the two tools to model these two different stages of the process. In particular, by the lattice-Boltzmann method, we will model the jet close to the nozzle in order to describe the formation of the initial straight path of the jet. And simulations obtained by this technique will be presented. Hence, the Lagrangian dynamic method will be used to model the bending instabilities, and more in general, the jet far from the nozzle and close to the collector. As a starting point, let me mention the technique used for the lattice-Boltzmann simulation. Here we have used the entropic lattice-Boltzmann collision approach, following the work by Ansumali and Carlin. This approach exploits a simple modification in the single relaxation collision step. In particular, the single relaxation time is here written as the inverse of the product of two parameters, alpha and beta. Alpha plays the role to avoid the entropy decrease, computed here as a H function, during the collision step. In simple words, we want to avoid the violation of the second law of the thermodynamics due to an over-relaxation time. And this is particularly important whenever we are dealing with low viscosity values. Then the beta parameter depends on the kinematic viscosity of the fluid. In this model, the extra force, which is essentially the electric force and the Shan-Chan force, is included in this case by the exact difference method, but it is possible to use other force scheme. By the Chapman-Enskog expansion, it is possible to show that the lattice-Boltzmann method can be used to numerically solve the equation here reported. In particular, since we want to model a multi-phase system, we exploited the Shan-Chan model. So the pressure is given as a function of a pseudo potential of the density, and the electric force, okay, here, is given by the Coulomb force plus a term which is depending on the gradient of the dielectric permittivity and the intensity of the electric fields. Since we need, in this case, a formulation of the permittivity as a function of the density, since you see there is the derivative of the permittivity with respect to the density here, we exploited the relation given already by Cooperstock and Medvedev, here reported in red, okay? But there are other possible relations that can be used, for instance, the Clausius-Mossotti. Further, we have to solve the Poisson equation in order to compute which is the value of the electric potential and the electric field. There is an important point that should be highlighted here. In this framework, we are dealing with fluid that can be considered at the same time as poor conductor, leaky, dielectric. In practice, these liquids show a conductivity which is just a bit below the conductivity of the water. The water has a conductivity around 10 to minus 4 in Siemens per meter, while this polymeric fluid have a conductivity 10 to minus 5, 10 to minus 6. So if we compute the electrical characteristic time as the ratio between the permittivity and the conductivity, and it is possible by doing conversion in centimeter, gram, seconds, but this is not important. we can assess this time in a range between 10 to minus 5, 10 to minus 6 seconds. And if we compute this with the characteristic hydrodynamic time, here computed as the product of the dynamic viscosity plus the times the radius and divided the surface tension, and considering that in this context usually the viscosity is high, around 1 Pascal per seconds, we can obtain a characteristic time of tenths of milliseconds. So in this context, we can, as an approximation, neglect the problem of the diffusion of the charge carriers in the liquid. However, it is important to highlight that only in such condition we can do this assumption. Otherwise, the convective diffusion of the charge carriers should be explicitly described, for instance, by the model introduced by Kupperstock and Mendeleev in their pioneering work of the 2006. So only under this assumption we can model the charge density directly over the interface. In particular, since the fluid is behaving as a poor conductor, we can assume that the largest part of the charge will be lying on the interface of the droplet, and indeed we add the charge by using a functional form of the gradient of the density. Here we are exploiting the gradient of the density just to localize the position of the droplet interface. However, in this description, there are effects that are neglected. One of the most important is the fact that the charge density usually increases as a function of the curvature radius, and this is something which is extremely common. We know that, for instance, the charge density increases on a needle tip. So we use a theoretical observation provided by McAllister, and in particular, we use a relationship between the charge density and the curvature. Hence, by adding the correction term for the curvature in our model, and for instance, simulating a charged droplet moving under the effect of an external electric field, we can observe the difference in the charge density when we use or we not use this extra term. And in particular, we note as the charge increase in correspondence of the smaller curvature radius when we compare this density with and without this extra correction. Hence, we are in the condition to proceed with the simulation. Here, I report the simulation with the parameter taken from the polyethylene oxide. We can observe the initial formation of a droplet when the movie will restart. Okay, this is the initial formation of a droplet. Then we can see a stationary regime describing the straight path of this jet. The simulation was performed in collaboration with Sauro and Pisignano, but also with Simone Melchionna and Andrea Montessori. So we can compare the obtained stationary regime with the experimental observation provided by the group of Professor Zuzman for a similar polyethylene oxide polymeric fluid. Here we can recognize a general good agreement among the numerical and experimental results. Further, we have extended the ability to simulate non-Newtonian fluids, which is an important key feature in presence of the polymeric fluids, which are usually pseudoplastic fluids. And in this case, we have adapted the strategy already developed by Pontrelli, Ubertini and Succi, where they exploit a relationship between the shear rate and the relaxation time. In that case, was in the context of the BGK collision. Here we have extended this strategy to the entropic model, and in few words, keeping fixed the value of the alpha parameter, we assess the beta parameter by an iterative procedure, in practice starting from an ansat viscosity value. We obtain a first beta, hence we compute the shear rate, then by the constitutive relationship, which in this case is the Carreau rheological model, we compute a new value of the viscosity, then from the viscosity new tau, so a new shear rate, and then we continue to proceed in this iterative way up to the value of the shear rate is below a certain threshold value. So in this case, we are able to span, to simulate over few values in the power index parameter in order to probe its effects on the dynamics, and in particular observing the velocity profile along the stretching axis. We can observe the presence of a quasi-stationary point. Okay, this is a particular point where the viscous force balances the electric pulling force, and we can observe as this point is depending on the rheological behavior of the fluids. Furthermore, we can also obtain information on observables that are difficult to resolve in experiments. For instance, this is the shear rate observed in a simulation with a power index equal to 0.75. And as an intriguing point, we can observe as the presence of the charge on the surface, on the interface, provides an important shear rate value in correspondence exactly of the interface. And this is extremely interesting because in previous theoretical works by Oman and Alexander Yarin was advanced the hypothesis that this shear rate can contribute to stabilize the jetting regime. Although these important findings, we have to recognize that the lattice-Boltzmann is not probably the most suitable method to model the jet far from the nozzle and close to the collector, at least in its standard form. For instance, without using any sophisticated techniques like non-uniform grid or multi-grid, if we suppose to have a jet radius equal to 0.1 micrometers close to the collector, and considering the typical distance between the nozzle and the collector, which is around 10-20 centimeters, only to storage a scalar field in a cubic domain would need several terabytes of memory. It means that LB cannot be used easily to model the jet close to the collector. As a consequence, we introduce the Lagrangian method. At this aim, we start by exploiting the momentum equation of a jet expressed as a function of a curvilinear parameter S. And here we have to recognize that the radius is not an independent variable, but it is related to the stretching ratio lambda, since we are assuming the conservation of the volume in the jet. In practice, we are neglecting the evaporation effects. And here I want just to focus your attention on these few terms. For instance, we see the derivative of the longitudinal stress along with the curvilinear variable S, another term which depends on the surface tension. There is this term which models the repulsive electric force, where E is the linear charge density, and here the final term is the electric force due to the external electric field. And if we split the jet into n segment, where each one is denoted by an initial S value and a final S value, we can split the jet in n segment. In practice, we have to understand here that if we use an S element, each S value is frozen on the jet and is evolving with the jet segment. In practice, this means that if I use a set of S value, I can discretize this equation in n segment. And in particular, if I assume that the radius is smaller than the distance between these bid, and it is possible to assume that this segment can be modeled as a particle-like, and we have to understand that we are completely free to choose the discretization. So this is just a condition that I want to respect. So under this condition, the jet can be represented as a set of bits, where each bit is a segment and each bit evolve in time according to several force terms that here are reported in the discrete form. And we can see, for instance, again, the difference in the longitudinal stress, exactly like in the continuous form, a term which is the repulsive Coulomb force, the external electric field, and a term modeling the surface tension. So now we are in the condition to write the set of equation of motion. Each bit has a set of these equation. And similarly, I can also add further force term. For instance, we added the lift force due to the air acting on a curved jet segment, which is this. Or for instance, we can also add a white noise to model the Brownian effect of the surrounding air on the traveling jet. More complicated, we have tried to model the air drag effects on the jet. To this aim, we started from experimental observation. Ziabicki, in particular, he investigated the dynamics of a pendant filament hanged to a fixed point in presence of an airflow placed in opposite direction with respect to the gravity force axis. And in particular, we use this empirical law which relates the drag force to the length of the jet, which is this L, and to the relative velocity between the jet and the air, plus other parameter like the density of the air and the kinematic viscosity. So by doing a bit of tricks, mathematical tricks, so converting in dimensionless parameter and variables, we can obtain a stochastic differential equation of the velocity that show the form of a nonlinear Langevin stochastic equation. Here, the nonlinearity is due to the power of the velocity, which is larger than 1, which is due to the empirical law. And it is also important to note the presence of an effective friction coefficient here, which is depending on the length of the jet segment. In few words, more stretched is the jet, larger is the surface of the contact between the jet and the surrounding air, and higher will be the drag friction. Apart the weird parameter S and P, which are experimentally assessed. As example, we reported the results of the stretching of a jet by these three different models. The first on the left side is without the drag effects and white noise. The second report a simple model following a linear Langevin model. And the last on the right side is the full form with the nonlinear term. And by probing asymptotic behavior of these three models, we can observe indeed as the nonlinear Langevin model present a clear different asymptotic limit, where the model without air drag follows the classical free fall regime. The second is scaling linearly with the time, and the last follows a power dependence set by the empirical coefficient. In this model, there is also a key point that should be addressed, that is the problem of the insertion of the jet at the nozzle. And in particular, by this method, we cannot describe the Taylor cone, but we have to assume that the polymer fluids is injected directly as split segments of the jet. Each segment is represented by a particle bead, and we have to define a rule to know when a new segment should be inserted at the nozzle. And in this case, if we denote L step, the length step used to discretize the jet in segment, we add a new bit whenever the last inserted bead has traveled a distance equal to 2 times the L step. The last critical point is that we have to consider that since the jet is stretching more and more when approaching to the collector, the distance between bits start to increase, and in simpler word, the mesh used to discretize the continuous equation of motion can be extremely coarse to the collector, but we have to consider that we are completely free to choose the mesh to discretize the continuous form. And moreover, we can also change the mesh during the simulation as the mesh become too coarse, for instance, below a certain quality criteria. Indeed, we exploit the dynamic mesh refinement approach in this context, and in particular, we use the old mesh to build a set of cubic spline for each independent variable. Then we define a new mesh with the desired resolution. Hence, the new values can be obtained by interpolation for the cubic spline, and we can repeat this process dynamically every a certain time interval. So all these tricks allow us to simulate the entire process. Here is the process of a fluid with the parameter of a solution of polyvinyl pyrrolidine. We can observe as the bending instability are well reproduced. Moreover, we can also monitor the fiber radius as a function of the curvilinear lambda parameter, which is on the right side of this slide. Here, lambda is taking value equal to 0 if we are close to the nozzle, and equal to 1 if we are at the collector. And it is particularly evident as the fiber radius decrease along the stretching path. Comparing few snapshots of the simulation left side with the corresponding snapshots taken during a real experiment, the right side, we can observe a general good agreement between simulation and experimental data in describing the instabilities. Again, other observable can be compared to experiment. For instance, we consider the angle drawn by the bending instabilities, the amplitude. And also in this case, we can find a good agreement with the experimental findings which is reported on the right side of this slide. So at this point, we have a useful tool able to investigate new experimental setups. And indeed, we have investigated the electrospinning process in presence of an airflow with opposite direction with respect to the electric field, also referred as gas-assisted electrospinning. And in this
Sorry,
case,
Marco, you have 5 minutes. Okay,
okay,
please.
yes,
Thank
yes. And for instance, we have investigated the effects of the velocity flow on the cone drawn by this bending instability. And I can skip this. Moreover, we can also analyze the morphological feature of the fiber as the fiber radius as a function of the counterflow velocity. And for example, here, if it is completely evident as a different magnitude of the velocity flow change the distribution of the fiber radius. But we can also investigate new experimental setups aimed to drive the topology of the fibers. For instance, the orientation of the filaments at the collector. Here we show a snapshot of a simulation where we have applied a rotating electric field close to the nozzle. There is also another oscillation mechanical of the nozzle itself, and by tuning the frequency of these rotating electric fields, we were able to observe the formation of different patterns of the filaments at the collector. On the right side here is reported the probability density of a jet segment to hit an area beams on the collector. No? So we can observe as the rotating with different frequency electric field provide these different patterns. Just as a last example, we have also investigated the electrospinning process in presence of particles. Usually particles can be embedded in the filament. This can be important for application like the photonics, where particles with different permittivity as gold or silver embedded in the filament, which is here acting as a waveguide, are used to produce new material with important photonics feature. Also, in this case, it is possible to obtain important information. For instance, here I reported the decrease of the fiber radius along the curvilinear parameter, and also we investigated the different distribution of the jet segment hitting the collector of during the process. As a future perspective, what is still lacking in my opinion is probably a multi-scale formulation able to take the best of the two computational tools. From one side, we have the lattice Boltzmann, which can be easily used to model the formulation of the spinning jet at the nozzle. On the other hand, we have the Lagrangian meton, which is a versatile tool able to investigate the jet far from the nozzle and close to the collector, and which in a successful way was shown to be able to describe the bending instability, and with a low cost in terms of computational core hours. Again, there are other possible important effects. One is the solvent evaporation, but there are work on this path. So, in conclusion, we presented an entropic lattice-Boltzmann method to model the formation of the jet close to the nozzle. Then we presented the Lagrangian model able to describe the filament far from the nozzle, which can be used to investigate the process also under different and new experimental conditions. And I want to just, how you say, highlight that more of the Lagrangian model are implemented on open source code. The name of this code is JetSpin. This work was done in collaboration with Sauro, Pisignano, but also with Ivan Kolutza and Pontrelli. And thank you for your kind attention. Thanks again to the organizer for the amazing efforts in this difficult COVID time.
Okay, thank you very much, Marco. Thank you for this nice and inspiring talk. Actually, we're just a little bit out of the schedule, so we have time for no problem. Just for a very quick question from the audience, if there is. Otherwise, we can postpone it to the coffee break and do it through the chat. Okay. If there are no questions, I would like to thank Marco one more time. Thanks, Marco.
Thank you too.
And now we start today's sessions. We have two sessions